Yes, so I thank the organizers to give me an opportunity to speak here. Yeah, so I will talk about some generalization of singular values to fairly general setting. To start, let me just start with the setup here. So I'm going to talk about the Pareto frontier. So suppose we are in the following situation. We have two norms on the vector space. So one norm I will call x, say, and the other norm I call y. So these are norms on, for simplicity, let's say a finite dimensional vector space, small to Rn. So now make a definition. So suppose you have, suppose we have some vector. So let me fix some vector. Fix some vector C or B. So suppose we have a decomposition. Is say A plus B, where say the norm of A is say small x, the norm of B is small y, and it has the following property that for every decomposition say C is A prime plus B prime, the norm of A prime with respect to x, norm, is larger than x, or the norm of B is larger than y, or if you look at the pair, it's just the same. So in that case, we call the pair xy Pareto optimal. And this decomposition and star is called, I just called an xy decomposition. Okay, so we can think of it as follows, that we want to write C as a sum of two vectors, but we want A to have small norm with respect to the x norm, and B to have a small norm with respect to the y norm. But clearly these are competing objectives. So if this norm is small, then B would have to be larger, and then the other norm could not be small. So the Pareto frontier is just a set of all Pareto optimal pairs.
So hard?
Yeah?
I mean, it might be hard to do, but so the geometric, I mean, this should be a nice geometric picture here that, so you're saying you have two centrally symmetric convex set. One is a set of everything that has, x norm less than or equal to x.
Yeah.
And the other thing, you have x norm, y norm less than or equal to y.
Yeah.
Saying that somehow you cannot decompose it in any different way as a sum from these two balls.
That's right, yeah. So you have like two balls that touch each other.
Right,
yeah.
I mean you extend one unit ball up to have norm x there.
Yeah, so maybe later if I have time I will show some pictures that illustrate this. But yeah, so this Pareto frontier, this looks a little bit like this. So here is the norm of C with respect to x, and here's the norm of C with respect to y, and then some optimal pair would be a point on this graph. So this is a graph of.
That's the image under D.
Sorry.
B or C. That's
So this would be the point xy.
But you're looking at an AB plane.
The norm,
Or the
norm
norm-
of
the
A
norm-
is
the norm
X and
X.
C is Y.
Yeah, so x is the norm of A and y is the norm of B. Yeah. So this is a graph of a strictly decreasing, convex, continuous function from this interval to that interval there. Yeah, so that's the Pareto frontier. Now I'm going to look at a slightly more special situation. So suppose, so now there's something I call the Pareto subfrontier. So suppose the vector space is now equipped with an inner product. And let's also suppose that these two norms are dual to each other. So that means that in particular we have the following inequality always. For any vectors a, b, we have this inequality. And moreover, for every a, there's a b for which we have equality, and for every b, there's an a for which we have equality. So that means that they're dual norms. So then the following statements are equivalent. So, oh sorry, forgot to say, but of course, we actually, beside these two norms, we have a third norm, right? So the third norm, which is sort of like an L2 norm, it's sort of given by the inner product, right? So you just take the square root of C inner product with itself. Okay, so now we have three norms, x, y, and 2. So C is a plus b is an x2 decomposition. Okay. So that means that here I'm using the x norm and here I'm using the L2 norm. C is a plus b is a 2y decomposition. And third, a, b, we have equality here. So these three things are equivalent. And so now what we can do is, so what is the Pareto subfrontier? This is the set of all pairs, norm from x, norm of y, b, y norm of b, where C is a plus b is an x2 decomposition. So that's slightly different because you see here I take an x2 decomposition, so this is with respect to the x norm, this with respect to the 2 norm. But what I'm plotting here is the x norm versus the y norm, okay? Not the x norm versus 2 norm, but x norm versus the y norm. And so the way this looks is you sort of get a similar graph. So also something like this, and so maybe it looks like this. So this may be the subfrontier. So it's sort of behind, right, the frontier. So that's how I call it. So again, this is a graph of a function. So a graph of strictly decreasing continuous function. It does not, it's not always convex, but it cannot be, in some sense, not too bad. But okay. Now, if you look at the subfrontier, it's a sort of nice because it gives you a lot of information. So if so let's say this is the subfrontier. So now I could take some point here. So that point corresponds to some decomposition. So this is maybe x, which is the norm of A, and y is the norm of some b, right, corresponding to some x2 decomposition. So let's see. It's an x2 decomposition. So actually, if you look at this area here, this area is exactly half times the 2 norm of 2 squared. This area is exactly half times the b norm square. And this area is sort of this inner product, which is also the product of x times y, right? That's the third condition. And the total area, you can see, is a half times the 2 norm of c squared. So in this one picture, you can sort of see the x norm of A and the 2 norm of A and the 2 norm of B and the y norm of B and the norms of C, etc. So this encodes a lot of information. We say that a vector C is tight if the frontier and the subfrontier are the same. So, in general, they don't have to be, but in some interesting cases, they are. Okay, so let's now go to singular values. So I'm going to look at the singular value decomposition, but I'm going to look at it in this context. Okay, so so now V is say space of say P times Q matrices, and for matrices we have various norms. Well, first of all, if I have some matrix, right, then it has a singular value decomposition. So that looks like this. C is right like this. U1, D, U2 transpose. Oops. Where U1, U2 are orthogonal. And D is sort of like a diagonal matrix. Well, it may not be a square matrix, but where these lambdas are the singular values, or non-zero singular values. Okay, so we have a decomposition like that. So the first norm that we have, other than the sort of L2 norm or the Frobenius norm, is the first norm is the spectral norm, which is just lambda 1. So this is sort of the largest norm you can get by applying C to some vector of length 1. Now, a norm dual to it is the nuclear norm, and this is just the sum of the singular values. Okay. You can also see it as the trace of the square root of C transpose, right? So there's a positive or non-negative definite matrix as a square root. So these two norms are dual to each other. So how does this
super max
say?
in line with C of x. Lambda 1 is not a set, it's a super over that set, right?
Right, yeah. On max, finite dimensional, so. Okay, so let's see. Yeah, so first of all, in this case, the frontier and subfrontier are the same. So every vector is tight. Every matrix is tight. So another way of saying is that these x2 and 2y decompositions are the same as xy decompositions. Right? So that's what it means to be tight. And the subfrontier, so maybe I'll just draw it. Let's just take the case RS3. Okay, so it will sort of look like this, maybe here, and then like this. Here's lambda 1, lambda 2, say lambda 3. Now here the slope is -1, and here -2, and here -3. So if you then what you get here is like lambda 1 minus lambda 2, lambda 1 plus lambda 2 minus 2 lambda 3. And here you get lambda 1 plus lambda 2 plus lambda 3, which is then also the nuclear norm of C. This is the spectral norm of C. So, so you see, you can understand this subfrontier in terms of the singular values, or vice versa. So if you take, if you call this subfrontier F, if I plot negative F prime, then that will look like this. Okay, where you have here lambda 1, lambda 2, lambda 3. So this is a bar of length lambda 1 and width here 1. Okay, so this width here is sort of the multiplicity. So what we learn is that the subfrontier encodes the singular value decomposition, essentially. So all the information from, you can just look at the subfrontier, you get all the information. So now it's a natural thing to do this sort of in a more general setting, because all these definitions, they work in a very general setting where you have basically some vector space with an inner product and then two dual norms to each other. So that's a very general setting. Now, you might get some kind of pathologies if let's see. Oh, maybe before I continue, maybe I should also say how these decompositions look like. So what is the decomposition of C? These XY decomposition or X2 decomposition. So if so, this decomposition may look like this, where A is U1, say E U2 transpose. So, and this has now singular values mu1 up to mu r, where this mu I is the let's see, the maximum of lambda I minus x and 0. So in some sense, there's the small singular values you make 0, and in fact, the largest values you actually decrease a little bit. So it's sort of what they call soft thresholding. But it's almost so this is sort of almost what they call principal component analysis. So you use, for example, if you have a matrix and you want to approximate it with a matrix of low rank, then you can use the singular value decomposition in this way.
So the inner product is just like A, B transpose square rooted.
It's a trace of a, yeah, so it's trace of A, B transpose. It's just the inner product if you just view it as a vector space and if you identify it with Rn in a natural way. Okay, so now I guess generalized singular values. So we go back to the general situation of section 2, where we have just a vector space with the inner product and two norms dual to each other. So as I mentioned before, this subfrontier doesn't have to be convex. So then what that would mean is that if you differentiate, I take the negative of the derivative, then you might get something that's not necessarily decreasing, and then it would be kind of strange what kind of multiplicities you would get. You might get negative multiplicities. So let's just, but in a nice situation, so if C is tight, remember that means that the frontier and the subfrontier are the same, then the subfrontier or frontier, it's the same now, is right. So if the same, it's already clear it's convex, right? So it's convex and also piecewise linear. And that's actually quite strong. So here it's actually perhaps a bit surprising that this is piecewise linear, because if you look at these unit balls, they're not polytopes, right? They're orbitopes. So these are in many ways very round things, but nevertheless, this graph is piecewise linear.
But I guess that's partially because the A and B you find are really they're the same U1 and U2. It's really just the L1 and the L infinity norm.
That's right, yeah.
It's acting on there, as is sort of controlling these norms here.
Right. Okay. So this actually allows us. So that allows us to define singular values. Multiplicities. So since this graph is, if it's piecewise linear, then I get a step function that's decreasing here, and then I can define singular values and multiplicities. Now it doesn't have to be that the multiplicities are integers here. So that's maybe one pathology here, but other than that, it's nicely behaved. And some other nice properties are that if C has singular values, so in the case where you have tightness here with multiplicities, say M1, M2 up to MR, then all those norms also have interesting interpretation. So the X norm is just lambda 1. The Y norm is the sum of the lambda i's with multiplicities. And the L2 norm is the square root if you take the sum of the squares counted with multiplicity. Okay. So this is exactly as it is for the singular value decomposition, right? So nuclear norm is the sum of the singular values, and I didn't write it here, but the L2 norm is the sum of the squares of the
So it's like
singular values.
Like L infinity weighted L1 or weighted L2.
Yeah, that's right. So, let's see. So that's something I call a slope decomposition. And it's sort of related to this notion of tightness. So first of all, what do I mean by the slope? The slope of an element C is just the quotient of the y norm and the x norm. Okay. So, I guess it's right here. So an expression like this is the slope decomposition. If it has the following properties, if we take Ci, Cj, the inner product, and this is exactly Ci norm x times Cj norm y for I less or equal than j, and we arrange them such that the slopes are strictly decreasing. Sorry, yeah, I think so. So then C is tight if and only if it has a slope decomposition. So this allows you to sometimes to show that some vector is tight. And in fact, if you look at say the subfrontier, then it's sort of this picture sort of like this here, where you have here C1, C2, and C3. So this is sort of the subfrontier for C1, this is subfrontier for C2, and this is a subfrontier for C3. Okay. Anyway, so that's okay. Now let's go to tensors, because that's what we're particularly interested in. So I think I'm at 5 now, but anyway. So let's apply this to tensors. So for tensors, so let's say V is a sum of a tensor product of vector spaces. Let's say that each of these vector spaces has an inner product, and then V inherits also an inner product. So we have an inner product on V, and we have also two dual norms. So the spectral norm here of a tensor would be, so if you take the maximum of T V, where V is a pure tensor, so that, I mean a rank 1 tensor, with norm of V is 1. Okay, you can see that this is sort of the generalization of the spectral norm of a matrix. And the dual norm is again a nuclear norm, so maybe I call this norm X and norm Y of T. It's a dual norm, so this is the nuclear norm. So this is the minimum or infimum, but it turns out it's actually minimum. So of sum of the lengths of vectors, where T is the sum of the VI's, and these VI's, let's say I is 1 to R, VI's are pure tensors. So the most efficient way to write T as a sum of pure tensors, that's the nuclear norm. And again, this generalizes the nuclear norm of matrix. So then these two norms, one can show they're dual to each other. So now it is not true that every tensor is tight. So there are examples of tensors where the frontier and subfrontier are not the same. But then there are also many interesting examples where they are the same. So let me just give some examples.
So do you take the standard Euclidean inner product again, or do you take something else?
Right. Yeah. So I have here. Right. So this is just a standard Euclidean length. Okay. So for some people this might be misleading that I use a 2 here. This is just the. In this case, this is just We have an inner product on V that's inherited from all these inner products in each of those vector spaces, and and then you have a Euclidean length.
So a pure tensor is just the product of the products of the components.
That's right. Yeah. So let's see.
So I just want to make sure it's the same as in the matrix case as before, just so I can make sure.
Yeah, it is the same. Okay.
Just to clarify, so the unit ball on the first one is like the Segre orbital?
For this one, so that's the convex hull of all rank 1 tensors of normalized to rank 1. Yeah.
So that's the product of the uniforms.
So these are again, or that one is certainly an orbitope. Yes.
Can you say why is it that you must have a minimum? So there's a decomposition that attains this?
I think you can show that if these VI's are linearly dependent, say, that you can rewrite it so that without getting a worse thing here. So then you can show that you can bound R from above, and then so we can just keep R fixed but very large, and then it's probably some compactness argument. Find the dimension of vector space.
But you know that it's a linear combination of a minimum span of convex halves.
Yeah. All right. So one tensor that people are particularly interested in here is this tensor that's related to matrix multiplication. So maybe write like this: Eij, Ejk, Eki. You can sort of write it in such a nice symmetric form. And let me just write n. Although in the beginning I said the n had dimension, v had dimension n, but now it has dimension n cubed. Sorry, n to the power 6th. Sorry. So in this case, so these are say orthogonal. These are orthogonal, and these are orthogonal in the set of n by n matrices, and then so then T. In this case, T has singular value 1 with respect to, with multiplicity n cubed. Okay. And in some sense, in earlier work, I introduced a diagonal singular value decomposition, and this actually turned out to be a diagonal singular value decomposition. Let's do another example.
So is this tight?
Yes. So this tells you not only something about the nuclear norm of this tensor, but it actually also tells you a bit about how well you can approximate T with things of smaller nuclear norm. Okay, so you can say something about how well you can approximate this tensor with tensor of a small nuclear norm, or say small spectral norm for that matter.
What's the nuclear norm? Is it n cubed?
Yeah. So once you have the singular values, right, we can use the formulas to find the nuclear norm. So it's the multiplicity times the singular values, so it's n cubed indeed.
It's the only singular value. Yes. Okay.
And the spectral norm is 1, and L2 norm is n to the power 3/2.
Thank you.
Excuse me, I am a bit confused because the singular values should correspond to the critical values on the.
Well, my notion of singular value doesn't necessarily correspond to other people's notion.
The wrote now is cancelled, but you also wrote as critical value. No, maybe I misunderstood this. So this is a different slopes.
Yeah, I never said anything about critical values, so.
Okay, okay.
So his singular values are the coefficients of his singular value decomposition. So those are so by
Yeah. Yeah. So far I haven't really. I discussed not really a singular value decomposition, but something that I call a slope decomposition, which is slightly different than the diagonal singular value decomposition that I have introduced before, but they're closely related. So.
So what's again the spectral norm for this tensor? You said it's
1. Yeah.
1.
So that sort of means that. Anyway, well, maybe. Let me just go to the next example. Yeah.
First one is related to the singular value. The maximum one is exactly the spectral norm, right?
Yeah.
So,
This sigma is exactly.
Yeah. So this one is 1, and this one is okay. This is 1. Nuclear norm is n cubed. L2 norm. That's the easiest one to compute. It's n to the power 3/2. Another favorite example of mine, sort of this tensor where you take the sign of a permutation and then you take E sigma 1 tensor E sigma 2, and the E's are again bases of a vector space. And they have are normalized to have length 1. They're orthonormal bases. So this tensor here, it turns out it also has singular value 1 with multiplicity and factorial. So again, you can compute the nuclear norm and spectral norm. Spectral norm is 1, nuclear norm is n factorial, and L2 norm is the square root of that. Perhaps surprising, if I omit the sign here, and the singular value, it again has only one singular value, but it's not 1. It's, let me just, yeah, it's n factorial divided by n to the power n/2 with multiplicity n to the power n over n factorial. So note that the multiplicity here might not be an integer. It's at least a rational number, but actually, if you think about it, if you were to define any notion of singular value for which all these 3 formulas were true, then I believe that this is the only possibility, because we know that the nuclear norm of this tensor, say the spectral norm, is. Let me just see. Let me say it one more. Well, we can derive from these formulas. So the spectral norm is just, of course, this singular value. the nuclear norm is this product here is n to the power n over 2. And it's, you see the nuclear norm from this formula, it's certainly not clear that that this is the nuclear norm, because you would guess it's n factorial, but n factorial is bigger than this. So this is not the optimal way to write T as a sum of rank 1 tensors. And then the spectral norm, sorry, the L2 norm is again square root of n factorial. So you take this squared times that, and I take the square root, so that's that.
There's a riser identity for permanent and a Glynn identity for permanent. Is it possible that those kinds of identities would have something related with your slope decomposition?
Yeah, absolutely. It's the Glynn one that does. The other one does not. You have to take that formula. Yeah. And then you get indeed the right nuclear norm. One more example. If you have, say, a finite group and the order of G is n, and let's say that D1 up to dr are dimensions of the irreducible representations. So now you can also look at matrix multiplication in the group algebra, and that's basically given by this tensor. So say some G and G, H and G, E, G. So I'm using an index, a basis that's indexed by the group elements of the group. So I'll make it symmetric so that the product here is equal to 1. So this tensor has singular value n over di square root, with multiplicity di cubed. So that's for I is 1 to r. So this one actually has r distinct singular values, namely these ones, and with these multiplicities. So it's not always that you get this just one singular value. Now, in general, like it sort of depends. I mean, I think there are lots of tensors that do have that are tight and that have a singular value decomposition. But then there are certainly also examples that are not tight. So then you can still look at the Pareto subfrontier, but you could not really nicely translate it into singular values unless you allowed some singular spectrum that might just be continuous and not discrete, and you may have to have negative multiplicity. So maybe that's perhaps a little bit too pathological to accept, but okay. Now, finally, we can, so this is for tensors. There are many other situations where you have two competing norms. So I have some examples in signal processing. So maybe let's fire up this. Okay, so first of all, I just wanted to have here a little. So what Greg said earlier. So I have a little. So I have to explain what this actually is here. So, this is actually not the one I wanted, actually. Oh yeah, that should be the one. let me just stop it here. So think of this as the origin, and this here is actually the unit ball. And so this blue one. This is the other unit ball. So this is sort of the unit ball for the dual norm. So this is the, say, C, and now I'm looking at the vector here that's closest. So I take a point on this unit ball, and then I'm looking at the point that's closest to this C with respect to the dual norm. So this is actually an XY decomposition. And so this red line is sort of it traces all the XY decompositions. But now, is this one different? I hope so. Otherwise, I had 2 copies of the same wrong one. Yeah. So this. So this is actually the X2 decomposition. So this is actually. So here I take this is like a unit ball of a certain radius with respect to the X norm, and then the circle is sort of the L2 norm. So I'm looking just taking the point here that's on this ball that's closest to C. So that's the X2 decomposition.
Just to understand, but where is C in this picture?
Yeah, maybe I should have labeled them here. So C is over here, and 0 is over here. But you see, there's also a dual picture, because I can also take a Y ball around C, and now an L2 ball around the origin, and I get the same solutions.
So this is illustrating your earlier theory.
Yeah. So this is this duality here. Okay. Now let me just give some other applications. So one application is, so these are applications in signal processing. Let me make this bigger. So let me. So I'll have to explain what this is here. So let me just stop it here. So I have some signal here, and I have 2 norms. Well, for one norm is this sort of the L infinity norm, and the other norm is sort of where you take the second derivative and you sort of integrate that. Okay, and so that sort of means. So now I write this signal, which is like in this case the ECG signal, and I write it as a sum of this red function. That's a function that has a very small y norm, plus a function that has very small L infinity norm. And I can use this, for example, to denoise signals. So if I run this, the closer it gets, the less noise I filter out. Right, so now I'm not filtering any noise, but if I make this distance more and more, that means that this graph here becomes more and more sparse, where sparse here is here in the sense of being piecewise linear. So it has fewer line segments, and the other norm is then the L infinity norm. But I think I already went over time, so maybe I'll also stop here. I actually had one more, but maybe I'll just stop here.
Can you show your next animation?
Okay, thank you.
Sorry.
The other animation is sort of a 2-dimensional version of this. So that's actually image processing. So one norm is Yeah, so one norm is the L2 norm, that's just the usual L2 norm. And then there's also what they call the total variation norm. And that being small in total variation means that you get an image that is piecewise constant on. Okay, so if I run the animation here, let's see. Okay. So, okay, maybe stop it here. So after I denoise it, well, I didn't start with a noisy image, but anyway, then you see that now I get an approximation of the original image, but it's piecewise constant. Or, you know, the large regions where this function is constant. So, this is the so-called Rudin, Usher, Fatemi total variation denoising. It's a well-known algorithm for denoising images, but it can also view it in this context. Well, okay. Let me just a little further. So now I'm going back. So now you get more and more detail, right? But that's sort of the animation.
So what are the norms used in this one? It's the total variation.
Yeah, so one is the total variation norm. The other one is sort of a dual norm that's sort of more difficult to explain. So I don't really have a nice... in some sense, the one that I showed before with the ECG signal, that's in some sense also total variation, but in some sense I integrated the picture. So if you differentiate all the functions there, then this piecewise linear becomes piecewise constant functions. And you see the one of the norm was the L infinity norm. So in some sense you have to integrate this picture and then take the L infinity norm. That's sort of the other norm.
The singular values depend on the choice of the norm x and y, if I got it right.
Right.
And so can you recover the already existing definition or some already existing definition of singular values by choosing wisely the x and y norms?
Yeah, so the main example that I know is just the usual singular value decomposition. I think there's some other generalizations for like where you have two matrices, but I don't know exactly if you can.
The tightness is also depends on x and y. I mean, you can find some examples where it's tight for a choice of x, y, and it's not tight for another choice.
That's right, yeah.
Tensor, or I mean, not that.
Right, yeah. So it depends on the choice of these norms, but these two norms are very natural. I just want to point out one more thing. So in the image denoising, the norm is not tight, so not all the images are tight. So it actually can be that you denoise actually a little bit more, and in fact you get an image that's less sparse. It could happen. For the other example, where I was denoising this ECG signal, in that example the norm is tight. So that one has a sort of a very nice description, and you have these slope decompositions in that case. And in some sense, in that case, the rank sort of means the number of breaks you have in this piecewise linear function. So, yeah.
These decomposition of matrices into sparse plus low rank, does it fall under this framework?
You say a matrix is sparse plus low rank. So in that case, well, so of course the rank itself is not a norm, right? So instead of a rank, you would perhaps take an L1 norm, like use convex relaxation, and the other norm
Would be spectral, right? If you use nuclear, the other norm would have to be spectral.
Yeah. Yeah, so the convex relaxation of the rank would be the nuclear norm. And what? Oh, you said sparseness. So sparseness, yeah, right. So yeah, on one hand you have sort of the L1 norm on the matrix, and the other one is the nuclear norm. But they're not dual to each other, so it doesn't really fit in this sort of general framework. But you could look at this Pareto frontier, but there's no sub Pareto frontier there, because I don't think those norms are dual to each other with respect to any bilinear form. So.
Questions? Doesn't seem to be the case. Then let's thank you again.
Okay. So I would like to thank the organizers for organizing this. Yeah, for organizing this nice workshop. So Lakhen Lim, Henry Cohen, Jason Morton, and Giorgio Ottaviani. Thank you.